Hi, this is Darshan Senth and welcome to another video on differential calculus. In this video, we're going to be doing more practice problems. So it's been a while since we had our previous practice problem video, so I thought it would be a good idea to go ahead and do a couple more practice problems, especially since we've covered some pretty big concepts that are really worth doing some practice on. So the concept is the same. I'm going to be just doing about 5 examples, and I'm going to be talking through them slowly, sort of showing you my thought process behind them, so you can really get a good grasp of how what we're really doing and how we're applying the concepts that we've learned here. Okay, so I hope this video proves to be helpful for you. And I used one worksheet in preparing this video, and it'll be linked in the description. So if you want extra practice, that's another good place to go. I think they'll have an answer key up there as well. So make sure you check that out if you want some extra practice on this video. So that said, let's go ahead and get started. Alright, so find the first derivative of the following function. F of x equals inverse sine of x cubed to the fourth. So just as a little side word, the derivative of inverse sine, this is stuff that doesn't go away, so you still need to know all this stuff. The only thing is you probably won't see stuff like this as often. You usually see like 1 or 2 of these across your entire test. So anyways, it's good to know them. So as you can see here, just taking a look at this problem, it's very clear, right, that we're going to have a chain rule, right? Because we've got this function, this fourth power out here. We've also got this third power in here, and we've also got, of course, the inverse sine. So it's very clear, right, that we've got 3 different functions of x in there. So we're going to need to use the chain rule. So let's go ahead and put that down. Right, so we're going to be using the chain rule. So let's quickly go ahead and talk about what our 3 functions of x would be. Number 1, we've got x to the fourth, right? We've got x to the fourth because that's shown by this out here. Next, we've got inverse sine of x, or as you might have also heard of it, arc sine. I like inverse sine better, but arc sine works too. So that's our second function. Last but not least, we have that x to the third in there, x cubed in there. Right, so that's our 3 functions of x. So now let's go ahead and use the chain rule. So again, this is a good example of how the chain rule can be used for more than one function in your composition. So you don't just need 2. You can do it with as many functions as you need. So this is what we're going to do. So we're going to take the derivative of the outer function, then the next function, and then the innermost function. So that's what we're going to do. So the first thing we need to do is we're going to have to start with x to the fourth, right? And the derivative of x to the fourth just by itself is 3x to the 4x, my apologies, to the third, right? So that's what we're going to do here. So f prime of x is the derivative of everything, all right, the outermost function. So that would be 4 inverse sine x cubed to the third. And remember, we always preserve the inner functions inside, okay? And all of this would be times, what's the next inner function? It would be inverse sine. So what's the derivative of inverse sine? Well, that would be 1 over square root of 1 minus, and don't forget, it's not x squared, but it's going to be x cubed squared. X cubed squared, all right? So that's what that's going to be. And remember, you're keeping that inner function because it's you're dealing with a composition of functions, and that's just a part of how the chain rule works. All right, so that's our second function. Now our third function is x cubed, and the derivative of x cubed, of course, is simply 3x squared. All right, and that's all the calculus you need to do really here for this particular example. Now all we're going to do is just clean this up a little bit, so you'll basically finally end up with the following. So that would just basically be your final answer. And I've just cleaned this up a little bit here, and that's honestly not too much work. So that's basically what this answer to this problem would be. It's pretty simple once you've understood what the chain rule says, and you've identified the functions that you're taking the derivative of. Okay. Number 2. So this is It's a pretty tricky problem. It looks very simple, but it's actually a pretty tricky problem that actually incorporates a lot of the rules that we've talked about. It's just really interesting to solve. It's a little bit of a pain, but it's interesting to solve. I think it's really good to test all the rules we've learned so far. So right off the bat, we can't actually do anything with this in the form that it's in, right? Because x to the x, it neither fits in our power rule for a to the x. That doesn't work because the a is not a constant here, and it also doesn't work for our function, our regular x to some power, or it doesn't fit our power rule bill either. So now neither of these are going to work. So what we're going to need to do is we're going to need to go ahead and give this function a makeover. So we're going to give it a makeover. So by makeover, I don't necessarily mean get out the makeup, but what I mean is we're going to make this function look different. All right, we're going to make it look like something we can solve, something that fits what we know how to do. So what we're going to do is we're going to take this may seem a little bit abstract. I wouldn't expect you to come up with this at the first time. I didn't. So what we're going to do is we're going to say, all right, let's make this e to the natural log of x to the x. Whoops. Let's make that e to the natural log of x to the x. Am I changing the value of this function? No, I'm not, because e to the natural log is just basically like saying, I don't know, 2 multiply by 2 and then divide by 2. You're not actually changing the value of the function. You're just making it look a little bit different. So this is very similar to multiplying by a conjugate. We're just making it look different. We're not changing the value. So what this allows us to do now is it allows us to, like I said, give it a makeover and turn it into something we can solve. Notice now that by the properties of logarithms, we can go ahead and bring that x down right here. That's just a property of the property of logs. A general property of logarithms is that if you have an exponent in your logarithm, you can bring it out to the front of the logarithm, and that has to do with a lot about it's about the concept of the logarithm, which I will I have a whole another video on that, so I'm not going to talk about it here. But basically, this will rewrite to e to the x natural log of x. Now that is something we can solve using the chain rule. That's a chain rule right there. Now how is it a chain rule? Well, you've got an e to the x, so you've got an e to something, so you've got an e to the x over there, because you're taking a whole bunch of stuff with it, you're raising e to a whole bunch of powers, and you've also got that x natural log of x there. And how would you solve that x ln of x though? So how would you actually solve this? Well, this is a product, right? So this is a product of functions, so you're going to need to use a product rule. So this question really incorporates 2 different rules. We're going to need to use a product rule and a chain rule. That's kind of why I like this problem why I really liked this problem. I decided to incorporate it in this video, is because not only is it a little bit of thought to give it a remake, but it also involves 2 different rules. So that's what we're going to do right now, okay? So we start the same. We start with the chain rule just because it's the outermost rule. Always start with the outermost rule, all right? So always go from outside to inside. So first thing we're going to do is we're going to take the derivative of the outermost function, which is e to the x. Conveniently for us, that's just going to be e to the x. So y prime is going to equal e to the x ln of x. Again, that's just because the derivative of the outermost function is just e to the x times the derivative of x ln of x. Let's take a look at that now. So the derivative of x ln of x is, if you recall, the product rule would be d dx of x times the natural log of x plus, right? So that's the product rule right there. So we've got the derivative of x times the natural log of x plus the derivative of natural log of x times x. This stuff is gonna just come out to the natural log of x. That's just because the derivative of x is 1, and then that multiplied by natural log of x is just natural log of x. Plus, the derivative of all that is actually gonna eventually come out to 1. And that's because what you do here is you've got 1 over x, right? The derivative of natural log of x is 1 over x times x, because of that x out there. So these two are going to cancel out, and you're just going to be left with 1, right? So that's where the 1 comes from. So this natural log of x plus 1 is the end of that product rule. So putting everything together, we get that y prime equals e to the x ln of x times ln of x plus 1. Now we could take that forward just one step, just to simplify it a little bit further. And to that end, we could actually pull out this, take a look at this e to the x closer, and we could actually rewrite it as e to the ln of x to the x power. Okay? So, and that's just another property of logarithms, because you can, if you have, again, we're just doing this rule in reverse. If you have a product of exponents, you can just, it's basically that. If you have a product of exponents, you basically raise everything to the power of that exponent. When you multiply exponents, it looks like that. That's basically what it is. So these two would simplify out to just x, remember, because e to the ln of x is just basically x, because e and natural log are inverses. It's the same concept of how we started in the first place. So we're going to be left with, really, we're going to be left with x ln of x times ln of x plus 1. And that would be your final answer. You can't really simplify that any further. Right? So that's it for this example. I hope that was pretty interesting. I thought it was pretty interesting. And of course, don't forget this method of doing e to the natural log of x and bringing the exponent down. This is really going to come in handy, especially as you get to some more complicated things in the future of your math career. So keep this at the back of your head. It'll come in handy. Alright, so let's take a look at this example now. So first thing we got to do is let's identify what rules we'll be using here. So right off the bat, we should know that this is going to have a quotient rule, right? A quotient rule. How do we know that? Well, that's simply just because we have a fraction over here, and that's usually a really telltale sign that we're going to need to use a quotient rule. Now, we actually have one other rule that we're going to use here. Can you see it? Well, if you didn't notice, we actually have a little chain rule in here, and that's because of that guy right there. So we're going to have another chain rule here. And the reason for that, again, is just because of that little 3x in there. So while it's not going to be a really difficult chain rule, we just have to take that into account anyways, because that's a whole nother function of x, and we're going to need to deal with that. All right. So that's basically that's two things we need to take into account. And yeah, let's just go ahead and do that then. So our derivative, y prime, is going to equal the quotient rule. First, we're going to start by using a quotient rule to set that up. So the quotient rule is as follows. You might have heard the little jingle we learned to, you might remember the little jingle we used to memorize this. That is low d high minus high d low all over low squared, right? So let's go ahead and do that out now. So low d high means the lower function, right? So that'll be ln of 3x times the derivative of the upper function, which would be the derivative of sine of x, right? Minus high d low. So minus just the high function, which would be sine of x, d low, which would be the derivative of the lower function, which is ln of 3x. And all this over low squared, which is ln 3x squared. All right. So that's how we do that. Now let's just go ahead and take this piece by piece. So for starters, let's look at this part, right? So the derivative of sine of x is, actually let's start with the ln. The ln we just leave as is, right? The ln of 3x stays as it is, but times the derivative of sine of x, which is actually going to be the cosine of x. Alright, so that's one part of it. And all this minus the sine of x times the derivative of the natural log of 3x. So this is going to have two parts to it. So firstly, we're going to have the derivative of the outermost function, which is ln of x. We're going to have the derivative of ln of x, which is going to be 1 over 3x, again taking into account the 3x, times the derivative of the inner function, which the derivative of the inner function is 3. So we're going to have to take that 3 into account there. So this, as you can see, that's really the only place we need to take that chain rule into account, because we have the 3x in there. We're going to need to just tag on that 3's derivative in there. All right, so that's the chain rule. And now the denominator just stays as it is, because again, we're not doing any calculus with it, and there's no way to simplify it, so that just stays as it is. Now let's just do a little bit of tidying up here, right? So the 3's are going to cancel, so that's very convenient. But we don't like to have fractions inside fractions typically, so we like to clean those up a bit. So what we're going to do is we're going to multiply this entire function by x over x. Keep in mind, this doesn't actually change the value of this function, because it's the same thing as multiplying by 1, but we're sort of just giving it a makeover again, right? Like we saw in the previous example, we're just changing it a little, just making it look a little different. The value does not change, we're just making it look a little different. All right, so the x we multiplied here, which means the 1 over x will be will cancel out with the 1 over x, but it's also going to be multiplied to this guy right here. I actually forgot this in the first take I did of this, but the x would actually multiply to this entire section as well. So you're going to have another x over here. And then also don't forget the denominator, you're going to have another x over here, right? So basically that's where all these x's will go. Don't forget that, right? Don't forget your basic algebra. So now to conclude, we're going to just tidy this all up and just wrap this up. So this would be ln of 3x times cosine of x minus sine of x. Oh, and don't forget the x in front of ln of x. So it would be x ln of 3x cosine of x minus sine of x all over x ln of 3x. And this guy would be cubed. Alright, so that right there will be your final answer for this. So in this example, we're going to be using implicit differentiation. Alright, and the reason for that is just because we have y's and x's in the mix. Okay, so let's go ahead and derive each part of this. So we start just by, as I just said, by taking the derivative of each part. So we start by taking the derivative of x cosine of y plus the derivative of y cosine of x equals the derivative of 1. So as you can see, what we're really doing here is we're taking the derivative of both sides, which is mathematically legal because we're doing it to both sides. So notice that this is just going to equal out to 0 because the derivative of a constant is always 0. Now let's talk about this part here. So this is going to be slightly trickier. So the derivative of y cosine of x. Notice that we're going to have a product rule in there, right? So we've done some practice with the product rule, so I'm going to go through it pretty quickly. So we start with the derivative of y, right? The derivative of y, which is going to be dy dx times cosine, okay, plus the derivative of cosine, which is going to be negative sine, times y. Okay, so that's basically how this part would turn out. Next, we have this guy. All right, so here we have, of course, these two are connected by a plus. So Again, I'm going to go through the product rule a little bit. I'm going to go through that. No, I'm not going to write all the product rule out. I'm just going to go through it orally. So we have the derivative of x, which is going to be 1, times cosine of y, plus the derivative, plus just x, times the derivative of cosine of y, which would be negative sine of y dy dx. Okay, so now let's go ahead and find all our dy dx terms, and note that all of this is going to equal 0. Okay, so now the first thing we're going to do is we're going to find all our dy dx terms. So we've got one over there, right? We've also got one over there. Okay, so first thing we're going to do, all right? So first thing we're going to, now second thing we're going to do is we're going to move all non dy dx terms to the right? So basically what we're going to do is we're going to take all these terms that don't have a dy dx in them, like this guy and this guy, we're going to just shift them to this side of the equation, all right? So what we're going to be left with after that is negative x sine of y dy dx plus cosine of x dy dx equals, so if we're moving this to that, so we're going to add it, so we'd have you'd have a y sine of x, because we're adding it to this side, minus cosine of y. Okay, now you might see where this is going, so we're gonna, after this, we're gonna go ahead and factor out dy dx. So we're gonna factor out dy dx, and then we're gonna just solve for it. All right, so to factor out, we're gonna pull out the dy dx here, and that will, factoring that out will yield negative sine of negative x sine of y plus cosine of x equals that up there. And now all we have to do is divide both sides by this, by negative x sine y cosine of x, and we'll be left with the following answer for dy dx. So we'll be left with that dy dx equals y sine of x minus cosine of y divided by cosine of x minus x sine of y. The denominator is basically that stuff over there. So this would be our final answer, right? So as you can see, implicit differentiation by itself is very, very simple. The only time when it gets very, very complicating is when you have to use it in conjunction with these other differentiation rules, like the chain rule, the product rule. And especially once you start doing that, the algebra becomes very, very complicating. So that's why implicit differentiation can be such a pain. But the concept behind it really isn't that hard. Just tag on a dy dx at the end. And also, in case you haven't seen it, I have a good theory video that explains really where dy dx comes from. So if you should probably check that out. Right, so let's take a look at this example now. So this is a little bit more like something you'll see on an AP Calculus FRQ. Just to clarify, it's not actually an AP Calculus FRQ. I just put this together, but this is the general format of what you'll see. You'll have one piece of information over here, and then you'll be sort of asked questions about that, different questions that sort of address different concepts about it. You'll be asked to do many different things with it. Usually it's a graph or of some sort, or a table. You'll just be asked to do a lot of things with it. But anyways, let's go ahead and get started. So number one, the first thing we need to do is find the first derivative. All right, so let's take a look at that right now. So first derivative, and so this is going to be implicit differentiation right off the bat, because we see we've got an x and a y, but it's not very difficult, implicit differentiation. So it's just since there's no chain rule, product rule involved. So let's go ahead and take care of that right now. So 4x squared, so we just start by taking the derivative of each term as always. So ddx of 4x squared plus ddx of 3y squared equals ddx of 6. Okay, so this is going to equal out to 0, right? And now for the ddx of 3y squared, we get a 6y times your dy dx, and nothing fancy here, just simple power rule. Then you get your 4x, your 8x, apologies. Right, now solving for dy dx, you just move this over to that side. You get 8x equals negative 6y dy dx, and solving for dy dx simply yields dy dx equals negative 8x over 6y, which can be simplified to negative 4x over 3y. Okay, so that would be our first answer over there. Negative 4x over 3y equals dy dx. Alright, number 2. So find the points where there exists a horizontal tangent line. Let's talk about that for a second. So what does a horizontal tangent line mean? Well, let's think about what a horizontal line means in the first place. So let's take a look at this over here. So on this graph, a horizontal line would look something like this, right? So just look at this and tell me, what do you think would be the slope of that line? Well, the slope of that line, if you just look at it, well, it's not changing at all. So the y value is not changing at all, which implies that it's just got a slope of 0, right? So that, my friends, is the defining feature of a horizontal line. It's got a slope of 0. So therefore, the point where a horizontal tangent line exists is going to be the point where our derivative, all right, equals 0. And remember, the derivative is synonymous with the slope of the tangent line. And therefore, where dy dx is equal to 0, the horizontal tangent line will equal 0 as well. All right, so let's go ahead and get this done then. So dy dx, the dy dx we figured out was that negative 4x over 3y equals our dy dx, and so therefore we're going to need to set that equal to 0. So basic algebra just suggests that this is going to be 0 when x is equal to 0. Right? So you just set the numerator equal to 0 and you eventually get that it's going to be equal to 0. But this is not our final answer. Why? Well, because we need a point, right? We need a point, not an x value. We need a point, which means we need a coordinate. We need an x and a y value. So we know right away that we have two coordinates here. So we have 1 and we have 2. So both of them have a 0 in them as the x value. Now we need to figure out what that y value is going to be. All right, so to do that, we're going to need to plug 0 back into the original function. All right, so let's go ahead and do that right now. So this is going to be 4 times 0 squared plus 3y squared is going to equal 6, right? Now dividing both sides by 3 is going to yield that y squared equals 2. So y is going to equal plus or minus root 2. Sorry, that's not clearly visible, but that's plus or minus root 2. So we'll have root 2 and a negative root 2 over here. All right, and that will be our final answer for the points where there exists a horizontal tangent. And if you wanted to verify this, you could actually go ahead and graph this function, and you'll notice you'll get something in the form of like an ellipse, something like that. And you'll notice that at these 2 points, you actually have, you'll actually have lines like this. You'll actually have, it'll sort of be like the top and the bottom of the graph. So you'll have you'll have horizontal tangent lines. All right. So now next, find the points where there exists a vertical tangent line. Let's talk about that as well. So, like the horizontal tangent line, the vertical tangent line is also a little has to do with has something interesting to do with the slope. So, take a look at that. So, what do you think is the slope of that vertical line right there? What do you think is the slope of that? Well, it's the y values are increasing, but the x values are not. So that suggests that this is undefined, right? So it's undefined. So the m is undefined. Slope here is undefined, right? The slope of the tangent line here is undefined. So therefore, for a vertical tangent line, this means that dy dx is also going to be undefined. If we're looking for a vertical tangent line, it means we're looking for where our dy dx is going to be undefined. All right? So let's try to solve for that then, shall we? So, yeah, that's all we have to do now is just set the same procedure as above. We set our 4x over 3y, we take that. And when would this be undefined? Well, it would be undefined if we were to divide by 0, right? So if that right there were to equal 0, then yeah, the derivative would be undefined, and therefore we'd have an undefined slope of the tangent line, right? So therefore, all we have to do is set the denominator equal to 0, and simple algebra suggests that this is going to mean that y equals 0. Okay. Now, again, like with the previous one, this is only half our answer. So we've got 2 coordinates, right? And this time we've just got a y value of 0. We still don't know what our x is. So we're going to need to do the same thing we did before, plug this into the original function and solve for x. Okay, once again, it's not too difficult. So we have that 4x squared equals 0, plus 0 equals 6. And x is going to equal, eventually it's going to be the square root of 3 halves, or plus or minus the square root of 3 halves. Okay, so because when you divide by 4, you get 3 halves, and then you just take the square root of that. So your answer would be square root of 3 halves and negative square root of 3 halves. Sorry, that's a bit messy. I was just running out of space. Okay, so that's it for the first 2 examples. Now let's talk about the final part, which is to write an equation for the tangent line at the point negative 2, 2. All right, so like we've seen in actually the previous example video, like we did a couple of weeks ago, the equation for the tangent line, the tangent line equation requires 2 things. You're going to need 2 things to do this. You're going to need a point, and you're going to need a slope. Right? So the point is given to you. It's basically 2 and negative 2. The slope is what you get from your derivative, right? So the first thing we're going to do is we're going to find the slope of this tangent line at the point. So let's go ahead and do that. So dy dx evaluated at, what's it, neg 2 comma negative 2 is basically negative 4 times 2 over 3 times negative 2. And actually, if you think about it, these 2 just cancel out, and the negatives also cancel out, so you're just left with a slope of 4/3, which works out quite nicely. Alright? And so our tangent line, therefore, is going to be the following. If you put it in point slope form, you're going to get the tangent line is y equals 4/3 x minus 2 minus 2. And that would be your final answer for this problem. So yeah, that's about it for this practice problem video. I hope it was helpful. I hope it helped you nail in some of the concepts we've been talking about in this video, in past videos. So if you found it useful, please do consider subscribing. It means a lot to me, and also you can keep up with my work as it shows up. Also please do consider liking or sharing or just leaving me a helpful comment and just tell me how I'm doing. I always appreciate that kind of positive feedback, because honestly, these, especially for these videos, I want to tailor make them for to help students study the best. So that any feedback would honestly be really appreciated. So thank you so much, and have a great day. Best of luck with your studies.